In today's video lecture, we learn about molecular docking by using the software SwissDock. So, in previous lecture, we have seen how to undergo molecular docking by utilizing different tools like PyMOL, Pyrex, Chimera, Discovery Studio. But the main disadvantage of those software or of those process was that you have to undergo a lot of steps to conduct overall docking. But uh, using SwissDock, you can easily perform your docking within just some simple steps. Okay, so let's learn step by step. However, we have already learned that usually you need a ligand and a protein, okay, to be docked. So a ligand can be any of your compound. It can be your drug or your extract molecule, or any of your compound that you have found or isolated from any plant extract. It can be any other thing, or also it can be also a protein. Okay, and your target is usually a macromolecule such as protein or nucleic acid, DNA, etc. So first of all, in today's video lecture we'll see, let's consider a ligand. We'll see the binding of telmisartan, which will act as a ligand, and for a target we'll take dehydrogenase enzyme. Okay, so we can submit the ligand by providing a smiles or its SDF file, or you can also sketch this by if it is a very new compound. Okay, using Chimera you can also uh, draw the compound by CamDraw or any other software. Okay, so by any other mean you can have the ligand. Okay, so I'll show you how to download the ligand. So I will check tell me certain. Okay, so I will check the smiles account. You can see the smiles, so just copy this and paste this. Okay, so prepare ligand, click on prepare ligand. Then I will provide my PDB ID of my drug, of my sorry, macromolecule, that is protein, that is 7JWS. Okay, so this is my protein. So it is aldehyde dehydrogenase enzyme. So click on A. It may have a lot of chains. Okay, so with which chain you will interact, or you will see the docking, you have to select this. For example, in my protein there is only one chain, but in some other proteins like uh, some phospholipase or some pancreatic enzymes, there are a lot of uh, chains. Okay, so within all of the chain you have to select those which are very much suitable for docking, and for this you need to study a lot. You need to study literatures. Okay, then choose heteroatom to keep. So click on here. I actually don't want to keep the heteroatom. For this I'm clicking on none. So what are heteroatoms? It can be some ligands, it can be some water molecule within the protein. Okay, we have already seen this in our previous lectures of in the PyMOL or Pyrex. We have seen how to delete this heteroatom. Actually we don't want this heteroatom. Okay, for docking you can type this by this mechanism, or if you have the PDB file you can also uh, insert the PDB format as you wish. So I've just put this and now prepare target. So this is ticked. Okay, you can see the tick, that means it is ready, but it is not ready. It will take time. Just wait until it appears. Yes, it has appeared as tick mark. So this is ready. Okay, now define search space. Okay, uh, while we were using Pyrex software, we have seen that, yeah, in the Pyrex software there is box center or grid box. Okay, so this grid box is important because within the grid box your overall uh, docking will be performed. Okay, so this grid box has been set, you can see here. Okay, so now it's so now you have to check a lot of parameters you have to check, like number of RIC. So what is RIC? RIC actually is random initial condition. It means random initial condition. It tells the docking algorithm, um, like how many different or randomly altered starting positions or orientation to generate for your ligand before running the simulation. That means the more RIC you will have, the more would be your timing. Okay, so actually it is kept within one or two, because you need a high processor for running this. Okay, if you set this in 8, then obviously your docking time will increase, so I've just kept this in within one. Okay, usually it is kept within one or two. Okay, now you can click on show extra parameter if you wish. Just click on that. You can see here sampling exhaustivity, then cavity prioritization. So usually regarding the cavity prioritization, I have kept this as buried because I want to have a deep search of my binding site. Okay, so I have buried, keep this as buried. Then sampling exhaustivity, so it is actually as like as RIC. So if your sample exhaustivity is higher, then you need a very long time for docking. Okay, just I have kept this as medium. Then if you have any question, then you can just click on that. Okay, you can click on that. If you want to learn about this, the sample exhaustivity determines the initial ligand rotation angle. The lower the angle, the higher the number of the ligand process. Okay, so that means if you set this as high, then you'll have a very prominent data obviously, but it will take time. Okay, then cavity prioritization. Okay, actually it shows the protein cavities within which our drug will bind. Okay, just set this as usual. Then check parameter. Okay, click on check parameter. After some time um, it will be tick. Okay, then put your email. Okay, I'm just putting my email as usual. Then enter the docking name. So uh, yes, check parameter has been confirmed, and now you can click on start docking. So your all of the parameters have been set, and just click on start docking. Okay, so this page will appear. Submission date is 6 June. Docking name, then ligand has been shown. Our ligand smiles is here. Then target is 7 GWS modified. You can see this is modified. Okay, energy minimized. So whenever we are performing this in Pyrex or PyMOL, we have seen that energy should be minimized, and there are a lot of steps. Okay, then box center, box size has already been shown. Okay, this is the box center, the grid box position. Then docking method. Okay, that is AC means attracting cavity score. Then sampling exhaustivity, that has been set as medium for our timing. Then cavity prioritization is buried. Okay, the number of RIC is 1, because the more the number of RIC, the more would be the uh, point. Okay, the more would be the duration. Then the job is estimated to take 27 minutes. So your overall docking would be performed within this 27 minutes. Until then you have nothing to do. And after uh, molecular docking, you result would be published in your email. Okay, you will get an email in your email Gmail ID. Okay, after 30 minutes I have received this email, and just click on here. Now you can see your result. Okay, so yes, this is my result. You can see your ligand, your target, then your box center. Okay, you can see your drug, that is your tell me certain. Okay, then your result. Now it's time for your result. You can see your result in that way. Just so now it's time for checking the binding. Okay, click on show protein surface. Okay, you can see the surface of your protein. Then whenever you will come down, you will find out number of displaced clusters, best member and by cluster. So you can have this by you can have 30 all of the AC score and all of the Swiss parameter score. Okay, so usually what are these actually? So the lower would be the AC score, the more would be the binding. Okay, then the lower would be the energy, that is the energy kilocalorie per mole. Okay, that is the binding energy. The lower would be the binding energy, the more stable would be the your binding. Okay, so we know within all of the value this is the lowest one, and this AC score is the lowest one. So what is AC score? AC score is attracting cavity score. Okay, so yes, we want it as the minimal. Okay, whenever you will click on that, so that is your optimized one, that is your optimized one. Whenever you will click on that, just click on that, then yes, you can see your pocket, binding pocket. Okay, just check this. This is your 3D surface. Okay, you can see your, yes, you can see your drug. You can see how your drug, that tell me certain, see that how uh, your drug is binding with the pocket. Okay, now we will see different interactions one by one. Okay, first of all, uh, show protein surface. You can see how your hydrogen bond, ionic interaction, then your hydrophobic interaction, pi interaction. Okay, one by one you can see all of them. First of all, you can see your protein, that is your drug tell me certain within this structure. Okay, and you can see your nearby uh, amino acid residues. Actually this is the drug. Okay, uh, you can separate the drug because the drug contains the atom in that looks in that feature, but your only amino acid structure is like that. Okay, your drug is only that, the middle one is your drug. Okay, now I will say different bond according to their color. Okay, first of all, check your hydrogen bond. So click on that. Okay, you can see your hydrogen bonds. So one of the hydrogen bond of the drug has been formed by this. Okay, you can see this is one of your hydrogen bond. Okay, this is a hydrogen bond. Okay, then another hydrogen bond is here, we can see. Okay, another hydrogen bond is here. So lot of hydrogen bonds, just click on that. Then you can see your ionic interactions. There is no ionic interaction here. Okay, no problem. And pi interactions. Then hydrophobic interaction, obviously there would have a lot of hydrophobic interaction because van der Waals force is working between different moieties and with the drug. Okay, then by stacking interaction. Okay, you can learn a lot by understanding the interaction. There can be have a lot of interactions with the drug. Okay, actually it will determine how effectively or efficiently this drug would bind with the receptor. Okay, then show the surface protein. You can see that there are a lot of pocket within the protein. Okay, but the drug has itself chosen its best pocket within which it can bind. Okay, you can see the pocket with which the drug has bound is the most sophisticated one. Okay, most efficient one. So you can also see a lot of clusters. Your drug your binding can have a lot of clusters. Okay, like in zero you have two cluster, In one you have four cluster, within two you have a lot of one cluster. Okay, within four you have five clusters. Okay, this is the cluster number and this is the uh, different position. Actually this means different position of your drug. Okay, so by different cluster your appearance can be in different way. Actually the one which will have the lowest binding energy would be the stable one, and the will have the lowest attracting cavity score point would be the stable one. So by that mechanism you can understand your docking. Okay, so now I will show you another mechanism. The thing that we have learned already is attracting cavities mechanism. Okay, but there are another mechanism for by which you can also perform your docking. So this is your front page of your server SwissDock. By this time we have performed docking with attracting cavities. Now we will see docking with Autodock Vina, and we will also see the difference between them. Okay, just click on Autodock Vina. Yes, now your docking will be performed via Autodock Vina. Then put your smiles. I put my smiles, then prepare the ligand, then put your target, then prepare the ligand. Okay, select the heteroatom and the chain, then prepare the target. Okay, then you can see your check your exhaustivity from 0 to 64. Okay, that as you wish, but the thing is that the more would be your exhaustivity, the more time it would take. Okay, so for this video I am showing you just within the exhaustivity one. Okay, then enter an email address. Okay, I'm putting my email address, then I'm putting my docking name. So now we'll see how docking with attracting cavities varies with docking with Autodock Vina, because by these attracting cavities we have seen different clusters. Okay, how different clusters is producing different interactions and different AC score. Okay, but within Autodock Vina we will not see those clusters. Okay, now let's see one by one. Now click on start docking. Just keep in mind this Autodock Vina will take less time, because uh, we are docking this by Vina. This will take very less time, because it will not form cluster. Okay, it will not form any cluster for docking in this, you can see. But uh, during attracting cavities it took more than 30 minutes, because it was forming a lot of clusters. Okay, but whenever you are docking this by Vina, it will not form those clusters and it will take less time. Now your result would appear here. Okay, you can see your result. Your target here method is Autodock Vina, that is not attracting cavities. Okay, the time has been shown here. Then you can see if you publish these results, please cite the following papers. Okay, okay, that is your ligand. Okay, so you can see your affinities. Okay, so there are a lot of models for your binding affinities. So model one is having minus 1.4. Okay, which score is very less. Okay, whatever the score is, it's not our issue. So you can see hydrogen bonds here, some hydrogen bonds, then ionic interactions, then pi interactions, hydrophobic interactions, you can see them. Okay, then show protein surface, so within which it has bound. Yeah, its position is much more different from those. Anyway, now you have to save this file. Just click on the zip, then your file would be saved. Click on that, then you can see your modified protein, your ligand pdbqt, then system pdbqt, vinadoc pdbqt. Okay, so actually which items you need. Actually, you need the system PDBQT and Vinadoc PDBQT. Both of them is needed. Remaining are not needed at this moment. Utilizing this two, you can perform your further uh, orientation. Okay, now I will show you. For that, you need to open your PyMOL software. Okay, first of all, extract all. Click on extract all. I have just extract all, no problem. So click on PyMOL software. I'll show you how to analyze them. Okay, skip activation, go to file, into open, the download. So your folder is Jahid 5. Okay, anyway, oh sorry. Uh, on Jahid 5, then just click on system PDBQT and Vinadoc PDBQT. System PDBQT is your protein energy minimized, and Vinadoc PDBQT is your energy minimized ligand. Click on open. Okay, you can see your Autodoc Vina software uh, docking result. Just click on zoom. Okay, so this is your overall binding. You can see your ligand telmisartan, and you can see your protein, that is aldehyde dehydrogenase. So this is bound very effectively. Okay, so you can have your surface view utilizing your um, pdb file. Okay, now all of the processing that you need to do, I have shown this in my previous lectures. Just go through this. Now I'm coming back to my original data that has appeared. So actually, what are the difference between autodoc vena and attracting cavities? Actually, in autodoc vena, it takes less time, and usually the result is not much more efficient, because you can see your calculated affinity is very low. That means binding is too weak. But if you take them as cluster, like attracting cavities score, then you'd have a lot of binding affinities. That is why we prefer docking by attracting cavities, that I have shown earlier. Okay, usually the atrodot vena result is done in comparison, or in respect of those docking that we have performed by PyMOL, Rex, or Discovery Studio, or Chimera software. Okay, so this is overall from my uh, topic on SwissDock software. If you have any confusion, please inform me in the comment section. Thank you.